I'm just going to start the talk, and people can drift in as they wish. First off, can I say good morning to everybody, and I hope you're all enjoying Vegas, because I'm sure Vegas is enjoying your money. Certainly did mine anyway. First off, some of you may have seen on the schedule that I was down as Managing Director of Cerberus Information Security. I'm happy to announce that Cerberus and At Stake have joined forces, so hence the At Stake PowerPoint presentation. Okay, I was told not to say and I've done it like in the first 2 minutes. Right, today we're going to talk about buffer overruns. It's simply looking at it on a basic level, showing you how to recognize one, how to exploit one, and this is hopefully with no prior knowledge of buffer overruns and what they are. So I know Dom, if Dom's around, was doing this, a similar talk a few days ago, so hopefully we're not going to cover too much similar ground, but let's get started anyway. Okay, as I said, the theme of this talk is being able to write buffer overruns with very limited knowledge. So I'm going to start with a quote by a man called Plato. He said at one point, "The only thing I know is I know nothing." And I would like to say that I know nothing, just before I start. Okay, so what is a buffer overrun and why should you care? Can I get a show of hands to see how many people have heard of buffer overruns and know what they are? So the majority of people in here, damn it. Okay, for those that didn't raise their hand, I'll give a quick explanation of what a buffer overrun is. Imagine a running computer program, sometimes known as a process. Obviously, for that program to be useful, it's got to deal with data. It will say, imagine a program that will simply say, enter your name. So you enter your name, and then it will print to the screen, hello, whatever you typed in. So it basically sets aside a buffer. Imagine a buffer basically as being a cup or something like that. Now, normally, this would be able to hold the average person's name. There's our buffer. The name goes in there, and it then does a number of different things. So I'm not sure if you've actually got this printed out, but consider 5 steps. Ask the user to type something. Set aside 100 bytes of memory as the buffer to hold whatever the user types. Wait for input. On getting the user's input, copy all of it to the 100 byte buffer. Read the contents of the buffer and print it to the screen. Okay. So where the overflow occurs, I'm not actually going to do it, but you can imagine someone enters too much data, the buffer's going to overflow, and it's going to start causing pyrotechnics or something. Now, when the overflow occurs, this is by someone entering too much data. So we've set aside a 100 byte buffer basically, and someone enters, say, 200 characters. In other words, tries putting 200 bytes into a 100 byte buffer. You can imagine what's going to happen. It's all going to overflow, and sometimes it will overwrite critical parts of other data in memory. Now, to explain that, this is going to be fairly disjointed and everything, by the way, so please excuse me, this is my first time speaking in public. I'm but a simple man and everything like that. Okay, so once the buffer's overflowed, it's been overflowed. Right, I'm just going to start reading from here. This is probably going to be easier. When you run a program, it becomes known as a process and is given 4 gigabytes of address space to execute in. Now, what that means exactly is it's like a playground. The computer operating system says, I'm going to give you 4 gigabytes of address space starting from addresses 0 down to FF, 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 FF. FF being hex for 256, by the way. Is that right? Again, So the best way to imagine this is, sorry, if I stand back here, can people hear me at all? Or do I need to speak up? Speak up, okay, I'll just try and stand here. Imagine you have 0 here and FF down here. When you run the computer program, basically, like say for example notepad.exe, it basically almost peels the data off that disk and slaps it into memory, okay? And that's the computer code basically. Now, as far as buffer overruns are concerned, there's another area of interest, another area of memory we're interested in. This is known as the stack, okay? So, continuing reading. As you'll be aware, most programs manipulate data in one form or another. Any that don't will be pretty useless. Accordingly, there's a block of address space that is designated as the area where data will be stored and manipulated. This area is known as the stack and dynamically shrinks and grows as and when desired. It's easiest to think of the stack as an expandable workbench, you know, something that a carpenter or a DIY expert or lover would do. When the stack grows, now this is sort of crucial. Sorry, we're talking about Intel platforms here, by the way, as opposed to Spark, so that's an important point. When the stack grows, it grows towards address 0. It will probably never get there, but just remember it grows from this way up towards 0, okay? Keep on doing this thing. Okay, if you would like to look on the screen to my right, assuming the bottom of the stack can be found at address 12FF0F, it looks like this before it grows. So we have the bottom of the stack here, and the top of the stack just above it. I don't know if you guys can see over there. So now, when it grows, it looks like this. You can see the old top of the stack and where our new top of the stack is. So that's what I mean by it grows towards address 0. But when it shrinks, it does that. So there was our old top of the stack, and now we're down to down there. So where is all this leading? Just setting the scene to explain how a program executes, and it's important to know the stack before I can explain it. As you'll see, this is integral to the understanding and exploiting a buffer overrun. A program can be really divided up into discrete chunks of code called procedures that each perform their own little task, but when combined as a whole, together they provide the program's functionality. Each of these procedures execute, and when finished, the next procedure is called, and it goes off and does its little bit. When the next procedure is called, and this is the key, the address following the address where the call to execute, sorry, starting again, because this is crucial. When the next procedure is called, and this is the key, the address following the address of where the call to execute, oh, typo. Okay, I'm just going to ignore this for the minute. When a procedure is called, basically, the address directly below it, that's pushed onto the stack. So when that procedure that has just been called finishes executing, the processor will go onto the stack and look for the address to return to so it can continue from where it left off. Is anyone not understanding what I'm meaning by that? No? Good. I'm sorry? Everybody. Right, I will go over this a couple more times. Okay, as I said, the computer code is broken up into discrete little chunks of code, basically, and we'll term these procedures. Now, procedure 1 goes off, does its bit of execution, and then it returns. Now, the next time a procedure is called, basically, when that's called, the address one down from that call statement, okay, that address is pushed onto the stack. So once that procedure has finished doing whatever it needed to do, that address is pulled off of the stack, basically, So the processor then jumps to that address and starts executing downwards from there. Yeah? It's just the saved return address. That's all it's doing. It's placing it on top of the stack. So, I've got to cut this ARM thing out. Consider the following. The top of the stack can be found at address 12FF04. The program is just about to execute the instruction that can be found at address 40-1F2034. Call procedure Q, which can be found at address 40209876. So here's the top of our stack. I'm pointing here, it's not going to be any good. We're looking at the diagram here. And then cut out a lot of the address space, and there we have our instruction at address 401F2034, call procedure Q. Process is about to execute this, okay? Procedure Q is much further down, and we reach the bottom of our address space. When the instruction at address 401F2034 is executed, our address space looks like this. As you can see, this is the top of the stack at the top of the document on the right here. The address one below, where the call procedure Q statement was called, it's been pushed onto the stack. Has everyone got this on their schedule stuff, by the way? Can you see this? For those people over on my left, if you can't see the board? Okay, cool. As you can see, the address after the address where call procedure Q can be found has been pushed onto the stack, on top of the stack. The reason this happens is so that when procedure Q has finished its task and is ready to return, the processor can pull this address off the stack and resume execution from where it left off. This address is known as the saved return address. From an attacker's perspective, if this saved return address could somehow be overwritten with something else, when procedure Q is finished executing, then the replaced return address is peeled off the stack, then it would be possible to get the program to execute arbitrary code. Imagine if somehow an attacker could overwrite this saved return address. It would then be possible to jump to an arbitrary address in memory of the attacker's choosing, thus radically altering the original intended path of the program's execution. Jump to the right place, and it might even be possible to execute computer code of the attacker's choosing too. Enter the buffer overrun exploit, and the whole reason behind this talk. Remember, the stack is also the place where data is manipulated. If we can find and cause a buffer overflow, it will be possible to overwrite the saved return address and gain complete control of the program's execution. Now, talking about web servers, you can imagine if we can find a buffer overrun on a web server and we can gain control of that program's execution, then from a remote location we can pretty much compromise that web server. So these are pretty handy for an attacker, not very good for someone trying to defend their web server. Okay, the first step in being able to exploit a buffer overrun, this is the first step in being able to exploit a buffer overrun, but why do situations that allow memory buffers to be overflowed crop up? More often than not, buffer overrun vulnerabilities are caused by poor or lazy programming, though in all fairness, they can simply be an oversight. Mudge, anti-sniff. Further to this, the programming language used to write the program is, in the first instance, is partially to blame too. Most overruns can be found in programs written in C or C++ and are usually caused by how C handles character strings. Other programming languages handle strings in a much more safe manner. Consider the following C source. Basically, if you have a quick look at this, all it does is say enter some characters, the program, when it's compiled, will then take that input from the console and then echo it to the screen. Okay. I've already said that. The problem with the gets function, which is in the C source code, is it keeps on copying data until it comes across a null byte. And if the first null byte happens to be 200 bytes away from the beginning of the string, then 200 bytes will be copied to the 100 byte buffer. The math simply doesn't go and the overflow occurs. A null is simply a byte with a numeric value of 0. Strings are terminated with nulls in C and C++. To denote where the string actually ends. Other C functions that lead to similar problems are strcpy, which copies the contents of one string buffer to another, strcat, which tacks on the end of one string onto the end of another buffer. Obviously, in both of these cases, if one buffer isn't big enough to hold the other, then an overflow occurs. There are other C functions that have similar problems, but we'll leave these for the moment. These functions all do, however, have safer equivalents. For example, strcat has struncat, and strcpy has strncpy, and gets has fgets. With each of these, you can specify how many bytes are to be copied to the buffer, regardless of where the string is null terminated. Whether the string is null terminated, well, it will be null terminated, but where that null terminator occurs, it's regardless. You say copy 200 bytes to the buffer, it will only copy 200 bytes to the buffer. Using these functions still can lead to problems. I won't go into those now, but providing you're checking your buffer lengths and everything like that, you shouldn't have problems like this. I won't go into sprintf. Putting this together, here's how we gain control of the program's execution. Point A. Program calls print message to a screen asking the user to type something procedure. This is the going over the C source there, just previously discussed, by the way. B, return address is pushed onto the stack. C, print a message to the screen asking the user to type something, procedure executes. D, print a message to the screen asking the user to type something, procedure returns to the address that was saved on the stack. E, program sets aside 100 bytes of memory on the stack for the buffer. Here the user enters 200 bytes of input. F, program calls the copy the user supplied data onto the stack, procedure. Return address is pushed onto the stack. The copy the user supplied data onto the buffer, procedure executes and copies those 200 bytes of user supplied data to the stack. At step H in the process of doing this, the saved return address on the stack is overwritten. J, the copy the user supplied data to the buffer on stack procedure returns to the address that was saved on the stack. Aha! But this has been overwritten with the user supplied data. Now here's the crunch. We now control where the program will return to, and if we overwrite this with an address in memory where our user supplied data can be found, we can possibly execute computer code of our choosing. We do this by putting together the code, putting the code in the data that we supply, and so when the program returns, it does so to our buffer and hence computer code. Then the code is executed. Simply, this is the buffer overrun exploited. Granted, the actual mechanics of exploiting the buffer overrun are more difficult, but before we examine the exploit building process, I'd better explain a few more things. For those wanting zero-day exploits, you'll just have to hold on a few minutes and then I'll get to the, well, it was publicly undisclosed, but it's all been printed anyway, so. Moving on swiftly. Everyone knows that everyone knows that a computer CPU or processor is the hardware component that does all the donkey work. It's the thing, for want of a better word, that executes a program's code. I keep on referring to the computer code, but what is this code exactly? Well, again, as many of you know, computers are logical beasts and work with numbers. To a computer, everything is seen as a number, a binary one at that. To be able to do anything useful, a processor needs to have a set of instructions that it knows and can blindly follow. For example, if it comes across the instruction hex 55, it knows what to do with it. It knows this because it has an instruction set. This instruction set is a list of operations that map to a numeric value or code. These are often referred to as opcodes. That's all computer code is, a list of opcodes strung together in a certain way that will produce something useful. When someone programs with these numbers, it's known as programming using machine code. In other words, the real language of what the computer talks and understands. When we program in a high-level language like C, our human-friendly source is converted into machine code. This is then executed by the computer. To help with the actual processing, a processor has little storage units on it called registers. These registers can hold values, addresses, and the like. Some of them have a special purpose. For example, the EIP register is known as the instruction pointer. It contains the address of or points to the next instruction to execute. Remember the stack? There are two registers that are there specifically to help with manipulate and keep track of data on top of the stack. The EBP register is the base pointer and contains the address of the bottom of the stack. Then there's the ESP or stack pointer, which points to the top of the stack. As far as this talk goes, these three registers are enough to know about, and as far as their purposes is concerned. For the time being, though, just note that we have a number of other registers available for our use, such as the EAX, ESI, EDI, and a few others. It is with the use of these registers that the work is actually done. Before you can manipulate any data, a pointer needs to be placed to it in one of these registers. Slightly more user-friendly than machine code is assembly language. By the way, a pointer simply points to an address in memory, so you can use that point as a reference. Say, this pointer points to my character string, so every time I want to refer to that character string, I'm just going to use this pointer because it basically points to it. Consider the following snippet of assembly code. Move into the EAX, the number 4, move into the EDX, the number 1, and add the two together. This simply moves into the EAX register the hex value 04, then moves the value 1 into the EDX register and finishes by adding the two together, deja vu, leaving the value 5 in the EAX. Simple really, eh? When we're building our exploit code, we'll be using assembly language, and once that's been done, we'll put it through the debugger to get the machine code equivalent. If this is the machine code we'll be putting into our buffer. So, with all of this, let's start building our exploit. In my opinion, there are 7 steps to building a buffer overrun exploit. 1, first find the buffer overrun vulnerability. 2, when found, find out how many bytes are required to overflow the buffer and overwrite the saved return address. 3, find a copy of our user-supplied data somewhere in the address space. Work out what address we need to use to overwrite the saved return address with to be able to get back to our buffer. Work out what we want to do with our overflow exploit, what command we want to run, and all stuff like that. Then write our computer code that will perform what we've decided we want to do in step 5. And then 7, test it. And if you start playing around with stuff like this, you'll probably have to keep on testing and retesting, going back to the drawing board, and lots of debugging. So testing is extremely important. As far as this talk is concerned, stage 1 is fairly easy. I'll be telling you where the buffer overrun vulnerability can be found. To find one, there are several ways to do it. You could read through the source code looking for slip-ups. That is, of course, if the source code is freely available. If the source code isn't available, then you could use a debugger or a decompiler. Or simply you could sit through and look at all areas where you can supply information and enter long strings and stuff like that and see if the overflow occurs. What you'll recognize Dr. Watson or something like that popping up saying there's been some access violation. If you find one of those, then you could have found a buffer overrun vulnerability. But you have to look at the right programs. Basically, you're looking for an overflow that is in a program that you can access remotely, or if you're looking to gain elevated privileges on your own machine, then examine all processes that have more access rights or privileges than yourself. We're going to look at a remotely exploitable buffer overrun that in most cases runs with system privileges. This is the nirvana of the buffer overflow hunter. A remotely exploitable buffer overflow that runs with system privileges means that we can compromise servers with ease. Such an overrun hands you the keys to the car, essentially. So where is it? Well, Oracle make great databases, and I mean that seriously, by the way. Their web front end leaves something to be desired, though. On its own, Oracle Application Server provides a web server called Oracle Web Listener. Oracle Application Server can also be layered on top of other web servers, such as Apache, Internet Information Server, and Netscape Enterprise Server, to enable the use of PL/SQL to provide the web front-end functionality that feeds into an Oracle database server. Regardless of whether Oracle Web Listener is in use, or OAS is layered on top of another web server, a directory called OWS bin is created. This OWS bin is by default accessible anonymously over the World Wide Web and contains a number of executables, many of which are shot through with buffer overrun vulnerabilities. As far as a physical location is concerned, on NT anyway, this virtual directory path maps to c:\/ORANT/OWS/4.0/bin. For example, one of the executables in there, oasnetconf.exe, has a buffer overrun in it. The overrun occurs when an overly long string is supplied after a -s switch and L switch. oasnetconf.exe -L -s long string. Now, when you're requesting this over the web, you would obviously after the question mark denoting the query string, question mark -L %20 -S %20 string. Okay, moving on to point 2. When found, find out how many bytes are required to overwrite the saved return address. The simplest way to find this number of bytes required to do this is test it. Without getting too technical, generate a string basically that has 4 characters like AAA, BBB, CCC, DDD, uppercase, then do the lowercase, then go through the numbers 0 to 9 and try that. If there's no access violation, slap in some A's. Keep on trying and you'll eventually get the access violation. So using this string here, there's starts off with a lot of A's, then it goes BBB, CCC, DDD, blah de blah. If we supply this string to OAS netconf, this will cause an overflow. Now we'll get a message pop up on our computer saying the instruction at address 7A 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 reference memory at 7A 7A 7A. We've overwritten the saved return address with our lowercase z's. This means that our buffer is 300 bytes. We simply look at the length of our string and chop it up and work out how many bytes we need. What we do now is slap on an extra number of bytes and overflow the buffer again. This time we'll debug it. Give me 2 secs, please.
Yep. There's a laser pointer.
Is that?
And there's turn the remote mic on too if you want to run it.
Okay, I'm just going to have to set something up here. Slipped my mind. At this point in time, so I'll just continue. Take it on faith for the time being. Okay, so we find a copy of our user-supplied data in the address space. Once again, the debugger has kicked in. Once again, the debugger has kicked in. I use Microsoft's debugger, by the way, that comes with Visual C++. We need to see if we can find our overflow string, and I suppose I should really demonstrate this actually.
do on this one.
Just checking it was. 7A, the address at 7A, 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 tried to reference memory at address 7A, 7A, 7A. So that's our overflow occurred. We've not actually exploited anything there, we've just caused the overrun. So I'm going to debug this now. Okay, the debugger's not got access to the desktop on here, so I'm just going to do it from a command line. It achieves the same result. Okay, we have the instruction at 41, 41, 41, 41, reference memory at 41, 41, 41, 41. A capital A, by the way, has a hex value of 41. So if we kick in the debugger now, okay, that's just saying we've got an unhandled exception in OAS netconf, and we have basically a number of different windows. The top window contains a list of our registers. The one below that contains just memory, and the one below that is our instructions. Now, the reason we had this access violation is because the memory at 41, 41, 41, 41 has not been initialized. There's nothing there, so we get the access violation. Now, looking at the registers, if we look at the ESP, if you up in the top right hand corner here is the ESP. The contents of the ESP is, for those that can't see it in the back, 120012C774. So if we go to that address, 12C774, we can see a whole load of our capital A's. That was our user supplied data. Now, to be able to execute arbitrary code, what we need to do is overwrite the saved return address, not with 41, 41, 41, 41, but with an address in memory that contains basically a call ESP or a jump ESP instruction, basically. What that will do is, once that particular procedure has finished, it will pull our address off the stack, the one we've supplied, go to that address, execute the code it finds there, which is call or jump ESP. It will then, the process will then go down to the address that the ESP points to and start executing downwards from there. Now, obviously, if we put computer code in here, it's going to start executing our code. Okay, so we've now found a copy of our user supplied data in memory. We can reference it by the ESP now. When you're playing with overflows, the first thing to do is look at every single register and go to that address basically and see if you can find your data. If you can't, then it's still possible to execute it, but it's so much handier if we can have one of the registers referencing our user supplied data. Okay, so now we need to work out what address we need to use to overwrite the saved return address with to be able to get back to our buffer. This is what I was saying about we need to find an address in memory that has a call ESP or jump ESP instruction basically. That those two different opcodes basically will say, as it sounds, basically jump to the ESP and start executing, or call ESP. It's the same result at the end of the day. Okay, remember we've overwritten the saved return address. In this particular case, we've overwritten it with capital A's. And the consequences of that and what this means. It means that the address that the processor should have returned to after the procedure had just finished executing, had called return, has been overwritten by us, the attacker. That means we can overwrite it with almost anything we want. I say anything because we can't have things like a null. Remember, they terminate strings in C, so we'd just be chopping our exploit string off if we had a null in there. If you're lucky, sometimes you can put it in certain places, but I'm not going to go into that now. A code to B can be found at the ESP in this case. To get back there, all we need to do is overwrite the saved return address with an address that contains either reiterating a jump ESP or call ESP instruction. These instructions do essentially the same thing. The processor will go back to the ESP and start executing downwards from there. This way, what will happen is when the finishing procedure calls ret, our address is peeled off of the stack. The processor then goes to this address to find its next instruction to execute, which will be a call or a jump ESP instruction. And when this executes, the processor will go down to the ESP and execute what it finds there. The only problem now is to find such an instruction in memory that doesn't contain a null. A few things can be done to help speed up this process. You can use something like ultra-edit, a binary editor, and do a search for FFE4 or FFD4, the actual machine opcodes for the jump and call ESP instructions. Look in every single DLL that's actually loaded into the address space of the executing program, the target program, and look in there. Ultra Edit, by the way, this is a screenshot of Ultra Edit. I've got kernel32.dll open. As you can see, you have in the center pane, where's this? This is actual binary data, and this is its ASCII equivalent on the right here. Okay, so doing a search for something like FFE4 or something, which is our instruction we're looking for, it finds one right here. Now, it's offset from this file at 32, 83, and a couple of bytes in. Now, what we would do is add this to the base address that kernel32.dll is loaded into. When I say base address, there is a preferred address at which DLLs are loaded into. Now, on Windows NT4, kernel32 is loaded at base address 77F, I believe. I just need to verify that. You use something like Quick View on NT4 to find this, by the way. Okay, this is Quick View. To run Quick View, right-click on a DLL or an executable, and just go down to Quick View. That's obviously if you've installed Quick View. I believe it is installed by default. Okay, so getting the base address is simply as simple as looking through this. Right here. I can't see it clearly. Looking for image base, there. Yeah? Look for image base, and as you can see, that's 77F with 5 zeros tacked onto the end. So that's the address at which kernel32.dll is loaded into the address space of the running program. So what we'd do is take that file offset, add it to that to produce Yep. Cancel this. I'm not even going to risk doing the maths in my head. Okay, so we have 77F32830. It was as simple as just doing that, stupidly. I'm very nervous, by the way. So we then go back to our debugging session and look around that area for an FFE4 instruction. Okay, and there we go, right here. We have FFE4, our jump ESP. So as you can see, this address here, 77F32836, there's no nulls in it, so that's handy. If we overwrite the saved return address with this address, then what will happen is once the ret is called, we'll come down to here basically, jump ESP will execute, and then we'll end up back in our buffer. So we now have our address we're going to use. So in our overflow string that we originally used, where we had overwritten with lowercase z's, we'll replace this ZZZZ with this address we've just found, with one caveat. We need to load it in backwards, okay? So in our exploit string that's currently being built at the moment, we'll put it in 3628 F377. So now we have a way to get back to our exploit code. We need to write it. So first off, we need to work out what we want to do with the overflow exploit. Before we can do this, we need to know what we want to do. First off, we need to consider where the overflow is. If it's an exe that is accessed over the web, this means it's going over TCP port 80, and we can make the assumption that the target is protected by a firewall, allowing incoming traffic over only ports 80 and maybe 443. Because these ports will be bound to another process, there's no point in trying to spawn a remote shell that will listen on these ports, and there's no point in doing it on any other port because it may be blocked by a firewall. We want this exploit to work on as many machines as possible, protected by a firewall or not. So rather than spawning a remote shell, we should code an exploit that will give us the equivalent of a remote shell, something that will allow us not only to run arbitrary code, but also arbitrary commands, without ever having to need to change the exploit code. What we can do is append a command, any command, to our exploit code and get our code to find this command and then execute that. So here is our overflow string with our exploit code ZZZZ, and then the command we want to run after it. You know, for example, cmd.exe/c dir. To do this, we'll need to understand something about the way arguments are supplied to programs. Basically, any arguments, and the whole command line for that matter, can be found on another area of memory called the heap. Like the stack, the heap holds data, sort of. On the heap, you can find the environment variables, the command line, and other stuff which I won't go into now. All we need to know is that whatever we supply to IAS netconf will be found on the heap, including our exploit code and everything we supply after it. What we could do is get our exploit code, what we could get our exploit code to do is work out where our command line is and step through this until it finds a special D word, one which we're going to create. And when it finds this, it knows everything after this is the command we want to execute. Don't worry, this will become much more clearer. Essentially, we'll get our exploit code to do the equivalent of the following C, the C code that is. We'll use get command line A to get the address of the command line. We'll then step through everything downwards from this address, looking for a special byte that denotes our command to run. When we find this, we'll supply the address, we'll supply this address to winexec. Winexec will execute a command, so when we supply the address of our command to run, it will go off and execute it. We'll choose our special byte by looking through our final exploit code and choose a value that is not in there. For example, if the special byte, if in our exploit code 7A, 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 7A isn't in there, we'll use that as our special D word. If we were to use a byte that was in our exploit code, then we wouldn't be able to find our command to run. So we write our computer code that'll perform what we decided to do in step 5. Going back to step 5, essentially what we're going to do, recapping, is the exploit code is going to stay the same, okay, always. We're then going to slap on the end of our exploit code a command to run. So if we wanted to launch Notepad on this machine here, we just type notepad.exe and tack that onto the end of our exploit code. However, we're going to delimit the end of our exploit code with a special byte, 7A, 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 okay? And we'll look through for that special byte, so our exploit code will know everything after 7A, 7A, 7A is the command you want to run. Okay, the first thing we need to do is preserve the stack, the state of the stack. If we don't do this, we could mess up our own exploit code, which we don't want. We do this by using what's known as the procedure prologue. Simply, it's push EBP and then move the ESP into the EBP. What that essentially does is pushes the address of the EBP, the base pointer, that thing that points to the stack, the bottom of the stack rather, onto the stack, and then bring up level the ESP and the EBP. So we're starting off from a common ground basically. We need to call get command line A first, so we'll open up kernel32.dll in quick view, look through the export table for this function. An export table is the list of functions exported by the DLL that other DLLs and executables can call. The export table tells us that get command line A can be found at offset 000-1A35 F5, and I'll show you here. Okay, this being quick view again. Here's our export table, and fortunately it's all listed alphabetically, so we go down to get command line A, and at the top there we see its offset. Again, we would add this onto the base address, and that's the address at which we can find get command line A. That is in the address space of the executing process. Okay, so we need to call get command line A first. The reason we do this is basically so we can find our environment variables and everything like that, our whole command line on the heap. Get command line A takes no arguments, so all we need to do is load this address into a register and then call it. This is the simplest method of doing it. Unfortunately, this is going to be tied to a particular service pack. This is service pack 6A on this server here. So we move into a register of our choosing, EBX. You shouldn't use things like the ESP, the EIP, and the EBP, by the way, for moving things and everything like that into, because they're quite important, you know, as far as referencing stack and executing code is concerned. So we choose the EBX register. We could have chosen the EAX, whatever. So we move the address 77 F1 A3 F5 into the EBX register. That's our address of get command line A, and then call EBX. Okay, that simply goes and calls get command line A. When get command line A returns, it places the address of the command line into the EAX register. Now we've got our command line back, we'll step through the string looking for our special D word that denotes where our command to run can be found. At this point in time, we can assume that 7A, 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 7A won't exist in the command line, so we'll just use that. So here is our assembly code. We add 1 to the EAX, move into the EDX, the D-word pointed to by the we add 1 to the EAX. We have, remember, in the EAX already the address of our command line. We're simply adding 1 to it, okay? We then move what's pointed to by the EAX into the EDX, and then compare it with 7A, 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 7A. And then if it doesn't compare, go back and keep looping until it comes across. But here we have a problem. We now have 7A, 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 7A in our command line. To avoid this, we'll have to do the following. Move into the ESI, FFFFFFF, and then subtract from the ESI 85, 85, 85, 85. What that will do is leave us with 7A, 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 7A in the ESI register. So then we just do a compare, pretty similar to the code above, but we just do a compare ESI with the EDX. That way we've hidden the fact that there was 7A, 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 7A in our command line. What this code basically does is loops until it comes across our special D word. It does this by incrementing the address in the EAX register by 1, then moves the D word pointed to by the EAX into the EDX register. It then compares the EDX with the ESI register, which contains 7A, 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 our special D word. Here we have another problem. Some web servers, such as Internet Information Server, will kick out an error message if there appears to be too far requests. And there would be in this case. What I mean by that is http://server/foo.exe?foo.exe. We'll get a 500 internal server error if we do that. A call to OAS netconf and the command we want to run would cause this kind of problem. So we'll have to obscure the command we want to run in the request. We do this by adding 1 to every character in our command line and then supply it to the server tacked onto the end of our exploit code. Because of this, we'll have to undo this as part of our exploit. First off, we'll move the pointer to our command line into another register, move the EAX into the EDX, then we go through another loop. If you have a look over that. What this code basically does is subtract 1 from the byte pointed to by EDX and adds 1 to the EDX to move on down the line. Moves a byte pointed to by the EDX into the EDI register, then compares it with 58 or an uppercase X. We're going to use this uppercase X to delimit the end of our command to run, basically. This code keeps on looping until it comes across this X. No puns about X marks the spot. Once this loop ends, we're going to need to get rid of this X. We do this by subtracting 58 from the byte pointed to by EDX. Now, winexec takes 2 arguments. A pointer to the string of the command to run, and a D word that denotes how the program should be displayed. For example, swhide is defined as 0. Freeze will just use this. It will also hide it from the console as well. To get zeros, we'll need to simply do an XOR with a register with itself. Once this is done, we'll push them onto the stack. So XOR ESI with ESI, push ESI. What this will do basically, excuse me. What this will do is create our zeros, our nulls, and push them on top of the stack. The second argument we need to pass to winexec is a pointer to the string of our command to run. This is stored in EAX at the moment. Well, not strictly speaking true. EAX points to our Zs, our special D word, so we'll need to add 4 to EAX and then push these onto the stack too. So add 4 to the EAX and then push EAX. So we've now pushed our arguments to winexec onto the stack. Now we have our arguments primed, we'll will load the address of winexec into a register and then call it. When it's called, it will look on the stack for its arguments. We do this the same way as we did for command line A to get the address, which turns out to be 77F1A986. In other words, we go through quick view, get the offset, add it to the base, and that gives us our address of winexec. This should now go off and execute when we call EBX. Once we've loaded that address into the EBX register, we then simply call EBX. This should now go off and execute the command we've slapped onto the end of our exploit code. To cleanly kill OAS netconf without causing an access violation, we'll call exit process. So likewise, we move the address of exit process into EBX and then call EBX. Okay, that's our exploit code. There's not much to it really. Now we have our assembly code, we need to get our opcodes. We do this by cutting and pasting the code into a simple C source file that calls the ASM function. So here's our code, just gonna So we put that into our C compiler. We then build that. And then we're going to debug it once it's built. And you'll see why in 2 seconds. So we step into it. Go to our disassembly, and as you can see here, we have our assembly. Push EBP, move the ESP into the EBP, but more importantly, we have here our numeric opcodes. These are exactly, this is what we'll be putting into our overflow string. Not things like push EBP, but the actual binary number for it. So we open up Visual C++, build it. Once we've built it, we debug it. By doing this, we can extract the opcodes. And this is our opcodes with our assembly. Now we have our opcodes, we can choose what our special byte's going to be. We'll stick with 7A, 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 otherwise known as 4 lowercase z's. All we need to do now is put everything together in an exploit program. First off, we need to fill up the buffer, then place 77F32836 as the value to overwrite the saved return address when the and then tack on our opcodes rather. We can also write our exploit program to convert the command line for us too. You know, add 1 so we hide the fact from the web servers that there's 2 .exes being requested. Okay, I'm not gonna go through this. You've all got it printed there, so if you want to read over this in your own time. This has already been built, so this is the attacker's box. This is the web server. Okay, that program you've got listed there When compiled, we'll do this. 10, 2, 2, 3, 4, 80. Okay. We supply the IP address or the domain name of the target server and what port the server is listening on, the web service. It then asks us asks us to enter the command to run. Someone give me an sorry? Notepad. Notepad.exe, okay. And there is notepad.exe. So essentially what we've done is sent our exploit code across, and it's executed and launched Notepad. One more. I'm sorry? I think it's set. Give me 2 seconds. I will. Well, yeah, I was going to say it's set to SW hide. If you, I've not actually tested it, but if you used 3 SW maximize, if it is going to be able to interact with the desktop, then use 3 as opposed to 0. Yeah. With this one, Internet Information Server is running as the anonymous internet account. So not with this particular one, but if I was using Oracle Web Listener, see, you have to code the exploit differently for Oracle Web Listener. Oracle Web Listener is running its system. So if you actually coded it for Oracle Web Listener, then yes, you could. This is on NT anyway. Internet Information Server and Netscape Enterprise. Actually, Netscape Enterprise Server, if you're using Oracle Application Server on top of that, and it's still running a system, then you should be able to do that as well. Do you want to see someone give me one more command, and I'll just run it? Sorry? Format. I don't think you'll be able to do that. Sorry? Yep. Okay. What we'll do here is go cmd/c. Let's think. I'm not sure if the redirection character will actually work, but we'll give it a shot. ccommand file.txt. Right, providing /c with cmd.exe, by the way, will execute the command to run, and then cmd.exe will actually go. Yeah, so we have a directory listing there of, so what I could do is create a batch file instead or something. Let's have a look. Sorry? It's not on that box. So. And you would need administrative privileges. Again, this is running as a low privileged account on this particular thing. Okay, this should have created a batch file called foo.bat. And foo.bat simply has dir in it. One method I suppose you could do is, providing you had the NTFS permissions to be able to write to startup folders and stuff like that, which if they're using FAT, well, there's no NTFS permissions, but if you've got a web server using FAT, then you're asking for trouble, really. Exactly. For example, say I have permissions to write to the OWS bin, yeah? I'll give this a shot. CMD, actually, no. .exe user. User readout to C command backslash around backslash WS backslash 4.0 backslash bin backslash user .txt. Okay, what I'm going to attempt to do here is run net.exe supplying user, which will give us a list of user accounts kind of thing, redirect that to a file in the OWS bin called users.txt. Okay. Yeah, and there's our user accounts, yeah. Bad permissions on that, by the way.
Let's start with the big sort of all the other devices and download the exe or control exe.
Sorry?
So we can make more site.
Well, yeah, but what we could do is, if we wanted to download stuff onto it, we could create a file called file.txt and put FTP commands in there, and then run ftp .exe -s : path to the text file. But that's providing the firewall will allow FTP out and stuff like that. So, okay, is there any questions? Sorry? Sorry, okay. Numeric opcodes, I compile my assembly code basically using the ASM function, build that. Yes, sorry. Okay, the gentleman down here was asking where did I get my numeric opcodes from. So the answer to that basically is I put my assembly code into the ASM function, build that using Microsoft Visual C++, step into it and debug it basically. You right click on the thing and show code bytes, yeah? Now with that we can get our opcodes, oops. For example, add 1 to the EAX in here. Add 1 to the EAX. Just below it, we can see the opcodes for that is 83CO01. It's quite faint. I'll highlight it. That may be easier. Yeah. Okay. So essentially, what we'd do is take these out of here, remove all the source code and stuff like that, and the addresses and all the other numbers. So we're left basically with our pure numeric opcodes, and then add them to a buffer. As you can see in the exploit program, the source code. For example, move FFFFFF into the ESI, BE here, yeah, put that into a byte of our character string. Our character string is what our payload, basically, what we're going to send to the web server, and then FFFF. So each byte of our exploit code goes into a character string on our exploit code program rather, which we then send to the web server. Okay. Before asking if anyone has any more questions, the protection for this, by the way, Oracle have provided a workaround for most of these problems, the OWS bin being accessible and everything like that. It is available from technet.oracle.com. You'll have to, if you're not registered there yet, you'll have to get a user ID and password. I also believe if you've got Oracle products, MetaLink has it there too. Any other questions? Sure.
First, a quick one. They market each as pointer 7A, 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 7A. Was that arbitrary? Just so we know?
It was arbitrary.
You could have done anything.
I could have, yeah.
Then, regarding the DLLs, do you look it up on the target machine?
Yeah.
To see where it was loading into. So is that a preferred loading spot?
Kernel 32 and NT DLL.dll, I believe, someone correct me if I'm wrong, will always get their image base. Other DLLs, if someone else is loaded there, then they might get pushed up, but kernel 32 and NTDLL.dll will always be given their image base addresses that they require, kind of thing, yeah?
It's only going to be select DLLs. That's what you want, right?
Well, yeah, specifically with kernel 32.dll on NT service pack NT4, we know it's going to be 77F. That's its base address, yeah, because that kernel 32 and NTDLL will always get their base addresses, I believe. As I said, if I'm wrong on that, someone shout out and say you're wrong. Does that answer your question?
Well, it's like if you have your own setup machine, you test check.
Yeah.
Kernel, this service pack,
Yeah. Well, the reason I did this, I coded it specifically for a service pack because rather than building a jump table and stuff like that, I was trying to keep it simple basically, so I'm hard coding addresses in. So if you can ascertain remotely what service pack they're doing, what they've got, you can modify the addresses in this code basically to work on any other service packs. You just need to know the exported addresses and stuff like that.
How do you develop fetch for stack it up?
Well, I've done a number of stuff with this, but stuff I don't want to make public. Yeah. Sure, at the back. Yeah, well, assuming you only have the web service available, specifically on Internet Information Server 5, there's a number of easy ways you can tell what service pack they're running. For example, even if you don't have the phone book service installed on your box, it will create, as part of the installation process of Service Pack 6, it will create these directories, these phone book service directories. So if you test for it and you get a 403 forbidden, then you know they've got Service Pack 6A, unless of course they've gone and removed it. But there's a number of different ways you can tell what service pack they're running and stuff like that.
Just run an OS.
I'm sorry?
Just run an OS in that.
Will that give you what service pack?
I'm not exactly sure.
Right.
It'd be good to try.
Yeah. Yeah. Any other questions? I would like to apologize, by the way, for this is my first time speaking in public, and a lot of hesitancy and a lot of ums and ahs, and I hope I haven't made it too bad an experience for you, okay? So.